Hello and welcome to my computer vision series. If you are new to my channel, in the recent videos we were building the foundations for actually deep models that can solve real-world problems. We've talked about convolutions, we've talked about parameter initialization and activation functions, we've talked about optimizers, batch normalization, residual connections. After all this time, we are finally ready to do our first real model. So this is what we are going to do today. Today we are going to train a ResNet model to solve Imagenet challenge. That's a huge data set, famous one. The challenge ran from 2010 to 2017. And we are going to train the model analogous to the winner of 2015 competition called ResNet 152. And I think it's really important to do that stuff, because if you just go through some other tutorials online, you will learn basic concepts in a sort of simplified form, and then maybe train some models to distinguish cats and dogs. But this is far from the real thing, trust me. When we are going to read the actual code of the model, you will see how much more complex it is because of the scale, because of the problems with the data, because of all of that. And to be the actual computer vision engineer, you need to be able to handle these problems. So this is what we are going to do today. Now, before we start, I want to say some minimal requirements that you will need to have in order to train the model in this data set. So the data set itself is 160 gigabytes. It comes in an archive. So before we start training, at least the way it is done here, you will also need to unpack it, which doubles the requirement of the disk space. Apart from that, I was actually able to train this network on my Mac M1, and it took roughly 5 weeks. And I also have a proper desktop PC with an NVIDIA RTX 3080. With that one, the model trains in roughly 1 week. Again, just single GPU, which is nice. If you read old papers from 2015, back then people had to install a bunch of GPUs, a bunch of high-end GPUs into one machine and do distributed training. Right now we get similar training times from just a simple GPU. So here we go. If you have that, let's go. If you don't, we can discuss how we can minimize this data set a little bit. But I encourage you to try to do it on real time. So here is what we did in our previous videos. We started with a simple PyTorch code to classify digits, low resolution, not really realistic. Then we went through convolutions, parameter initialization, activation functions, optimizers, batch normalization, and residuals. And today we are finally trying to tackle Imagenet with high-resolution images, a lot of classes. So if you don't know any of these things, please do check out my recent videos or just try to Google these concepts online, because we'll need them today. So here is the plan for today. First, I am going to talk a little bit about the challenge and the dataset itself, a little bit of history, and then we'll actually look at the images inside the dataset, discuss it a little bit. Then I'm going to go through the code of a ResNet model. So this is going to be the code from PyTorch open source implementation that might be a little bit different from what was going on in the original paper, but it is guaranteed to have roughly the same architecture and the same quality. Then we'll go through the training code. That is the thing that actually trains this model. So we'll discuss optimizer parameters, the data loading pipeline, the image transforms that we'll need to do. Then finally, since this training is going to take a lot of time, like a week at least, we are going to discuss how to debug and optimize training speed. And finally, we'll discuss the results, the accuracy we achieved, the problems with the data and the approach that we had, and the next steps to do in computer vision. Right, so the dataset. The Imagenet itself is just a huge database of labeled images. Currently, it has about 14 million images and roughly 22,000 classes. And this is about 2 terabytes of data. The most classical subset of it, called Imagenet 1K, which was the one used as a dataset for the famous Imagenet challenge that is talked a lot about in computer vision tutorials and deep learning tutorials. It is a subset of 1,000 classes from this dataset, which results in about 1.2 million images, which is 150 gigabytes. And so you can shrink it even further. So there are some smaller subsets, maybe with smaller images as well, like 100 classes or 10 classes, which makes the task of training a model on top of those a little bit simpler, but it's not as challenging, and you might lose some understanding of what is going on because of that. So I urge you to try the Imagenet 1K, because this is the most famous one, and also because it's big enough to be challenging. So first, a little bit of history of the challenge itself. And I want to talk about this because this history of challenge corresponds a lot to the history of deep learning itself. So the challenge started in 2010, and the numbers here correspond to top 5 accuracy. So the organizers of the challenge decided to go for top 5 because of some problems with the data. So sometimes it will have different objects in the image, sometimes it will have more complex task, like classify that this particular scene is from a restaurant. That scene might actually have a lot of objects like a cup or a plate, and so the network is not necessarily able to understand what we want from it. So because of that, we have top 5 accuracy. So if the network has managed to find the class we want along top 5 predictions, we consider that a success. And so the first 2 years of the challenge, 2010, 2011, were before convolutions. So people tried to apply just usual machine learning approaches, typically with a lot of handcrafted features, a lot of expertise, people trying to sort of look at specific classes and try to come up with good features that they can write the code to extract to be able to classify those classes. So I would say this is pre-deep learning approach. Then, and that was before convolutions. Then in 2012, the famous ResNet came out, which was the winner of the competition that year. And it achieved much better quality. And this network basically popularized convolutions. So before 2012, although convolutions were known to some researchers in closed circles, but no one really knew or understood them in the broader world. After that, after ResNet, convolutions became #1 tool in computer vision. So after this year, every winner, every network tried, mostly had convolutions involved. Now in 2013 and 2014, not much interesting from conceptual understanding was going on. The quality improved a lot. People experimented with different architectures, basically having the same tools, but then trying to combine them in various ways and solve the challenging problems of training these big models on big data set. And then 2015, we have batch normalization. So again, if you look at the original paper for batch normalization, which is not necessarily related to computer vision, they mostly talk about Imagenet, because this challenge basically gave a lot of researchers a challenging task and a benchmark to compare with other approaches. So batch norm came the same year, ResNet came a little bit after that in the same year, and ResNet introduced residual connections, and it was the winner of the competition that year. Now, after 2015, we do see some improvements in the accuracy, but again, there was nothing conceptually interesting. So just same approaches, trying to sort of reconfigure them, trying to train supermodels that combine several predictions and so on. So again, we will not talk about them. So today we are training the ResNet, the analog of winner of 2015, which should have roughly 5% accuracy. So here it says 4% because, again, to achieve better benchmark, authors usually used some extra techniques. So one of them is just training 10 models with the same architecture, with the same exact training code, and then taking the average prediction, for example. Another one is to take different crops of the image during testing. Again, applying the same models and then averaging out the prediction along the same crops, which does allow to win an extra % of accuracy. But then it sounds a little bit like a hack. At least it's not something we'll do in the actual production environment because it is complex, it takes a lot of computation. So we'll not talk about this as well. So the single model ResNet got around 5% accuracy. Okay, now let's take a look at the actual data. So the first important question is where to get the data. And for a machine learning engineer, this is really important because this data is value. You need to know these things. So if you just Google Imagenet dataset, the first link is going to lead you to imagenet.org, which is the original database with 14 million images. Now, they say that you can register with them, you can apply and ask them for access, and they will provide it to you within 5 days. So I did that like a month ago. They still didn't reply to me, so I'm not sure. It's also hosted on Kaggle. Let's just Google Kaggle. So on Kaggle, there is a 1K subset. So the famous Imagenet challenge, 167 gigabytes. For that, you can just register on Kaggle itself if you still haven't, and then just click download all. So this will download the archive with all the data. So this is how it looks like. So this one is unpacked. So on the top level, you have some CSV files with extra information. So we go here, for example. So this N02, 01, etc., etc. These corresponds to the class label. And then these 4 numbers are bounding boxes. This means that we can use Imagenet for object localization and object detection as well. So sometimes you would see more than one bounding box, which basically corresponds to many objects of the same class being in the picture. And as you can see, this file has 500K lines. So not all images have bounding boxes, roughly half of them do. And then if we go here, so I go down to ILS-VFC, again, image sets and annotations does not contain anything new. So some of them have just descriptions of the files that we're going to see. Some of them have bounding boxes as well in slightly different format. And then if we go down to data, to CLS lock, train, we see the actual folders, right? And the structure of this one in the bottom is the standard format for such image datasets. So this class corresponds to class labels. You can probably find somewhere in the text files what these labels actually mean. Or you can just sort of enter the folder and see for yourself. And so all images within this folder will have the same class. So all of these are dogs and moreover a specific breed of dog. And so if we just scroll through images, we can see that, they are realistic, they are high resolution now. The actual resolution for every image might be different. Some of them are bigger, some of them are smaller, which is one of the problems that we'll have to deal with. because tensors like to be of equal size every time. So we'll have to do something with that. So this one is for a different breed of dog. Here we have 2 dogs. So this is a good data set. It's challenging realistic images. On the other hand, it might not be challenging enough for some tasks. So for example, it doesn't have images with no objects. It doesn't have images in, I don't know, artwork or just random pictures of space or some medicine. So the network will not be able to even understand what is going on. So most of the images are of certain objects, mostly centered. So yeah, this is how it is. And now I'm going to my Jupyter notebook to actually try and load these images. So again, the format might be a bit interesting. So we have different folders, each folder corresponding to a class, and then within that folder we have the actual images. And yeah, another good detail is that it's just JPEG, so it's just an image you might have taken with your phone. It's not in some tensor format, it's just an image. So we'll see how we load that into our PyTorch. So I start with just importing the libraries, and I define the same function that will allow us to actually show the image, the image of a tensor. Then here I have my path to this innermost folder. So again, if I enter train, I get into this image folder, which is a collection of directories with classes. And I just confirm that it is correct. So the folders within this path do correspond to classes. And so here is actually just the copy of the code from one of the previous tutorials that loads MNIST data. So back then we haven't really talked about what is going on here, like what is transform and so on. So first let's change that to image folder. And then the root will be the training folder name. And the rest I can just delete for now. And let's see if it actually works. And yeah, it works. So basically, the datasets.imageFolder class is a class from PyTorch that allows you to load these image folder datasets, where you have a folder. Within that folder, you have a separate folder for every class. And within that one, you have the actual images. And it does it properly, meaning that it understands that the folder name corresponds to the class label. It knows how to convert that to the actual label that you want, and so on. And the dataset class itself is like a pandas data frame. So I can go ahead and just call the first element, and here it is. So right now it says PIL image. So it's a tuple of 2 elements, PIL image and the label. Every class has about 1,000 or several thousand images. So image number 500 will have the same class, but then image number 5,000 is a slightly different class. And so PIL.image is just the default class in Python to work with JPEG, to work with images. Now, if I add transform here, I'm going to add toTensor, which is the one we had last time as well. Now, instead of loading this PIL image, it will automatically convert that to tensor. So this one transform just takes the initial image format and just converts it to tensor with raw pixel values, which is what we need for training. In addition, we will have more transforms on top of that afterwards, because one of the problems we'll have to solve is that images are all of different size. So we'll need to do some resizing and cropping during loading of the data. And that, again, is just passing on different transforms here. Also, if you remember, the dataset itself is 150 gigabytes. In here, it was initialized in less than a second, which means that, and obviously such a big data set cannot be loaded into memory all at once. So what happens instead is this data set just knows where the files are, but then when you fetch the actual element, it will go and fetch this file, it will open the file, it will get the image, and then apply the transform to it. And that might be a problem again later on, because you keep opening these files, you keep getting the data from disk. That might not be very effective. Right. And now finally we have this show image code that can show us what it is, and it takes the actual image, which is the first element in the tuple, and the label, which is the second element of the data. And here it is. So here is the actual raw image. All right, now that we have our data loaded as an image converted to tensor, let's look at our model. So I'm just going to Google PyTorch ResNet. So this is the hub of PyTorch. So PyTorch developers try to reproduce models very close to how they were described in the papers using the PyTorch library. They also host the actual weights of the model. So if you need the model in real life, instead of training that from scratch, you can just download the existing model from PyTorch. This is not what we are going to do today. Today we are training from scratch. And here on this view on GitHub link, they point to the actual model code. So we are going to look at this code today. This is the actual definition of the model, how you can write that yourself in PyTorch. And yeah, I also want to show a little bit about this repository. So this one is PyTorch Vision /Torch Vision Models ResNet. So if I go up one folder, I will notice that they have a lot of various models for classification, like ConvNet, AlexNet, MobileNet. They also have some models for optical flow, object detection. So they have a lot of material here. This repository is one of my primary sources of finding out how things actually work, because this is the source code. This is stuff that actually works, and you can look at how it works. And finally, if I go to the root of the repository, so I go to vision /references /classification, for example, I also see the training code. So now how do you actually train this model? So unfortunately, the repository cannot contain the dataset. You will need to find the dataset first. But this repository has the actual training code, the parameters that were used to train the reference models. So here we can see the batch size that was used, the number of epochs. We see that the models were trained with SGD with momentum, with weight decay, with learning rate scheduling. All of that we'll look at a bit later. Right, so now let's initialize the actual model. So I do that because I want to be able to actually see model predictions before reading the code. It's always easier to read code when you have a working example. So this is how you can load the model without pre-training weights. So it's basically initializing it from scratch. Now, to apply that to our image, we'd also need to add some transforms and to pack the images into batches. So if I just go like this, like we did before, so I have my data set. So the data set allows me to get if I have an index, I ask the data set to return me an image with this index, and it returns me the image and converts it using this transform. But now I want to unite it into batches, and the data loader also converts it to an iterable, so something I can iterate with a for loop. So I initialize data loader with the patch size of params patch size, right? And then I try to iterate with this. So when I try to iterate, let's look at the error that we get. Now it complains that I've got a few images with different sizes, and I cannot sort of combine that into tensor. So we'll have to deal with that now. Luckily, the PyTorch hub that we've seen here actually provides with the transforms, with the proper transforms that we should use for evaluation. So here we can see that we do resize, we do center crop to tensor and normalize. So yeah, let's just first copy them to see if they actually work. Transform this. Right. So now I check if this works, and it does. Let's look at how the image has changed. So we started with just one transform that called toTensor, which basically converted the PIL image class to PyTorch tensor. Now we have added the transforms to make it composable into batches. So it does the following. First, it calls resize. So resize resizes the smallest dimension of the image to 256. So it uses some sort of algorithm to actually find out the values for the pixels. This is not trivial, but it's a known thing in computer science of how to actually resize images. So if you shrink the image, it will try to approximate the pixel values to show the same image, but with a slightly less number of pixels. If you enlarge image, so we had some images in the data set that are actually smaller than 256, it tries to sort of come up with more pixels that would look the same as this smaller pixel image, but the quality obviously will not be so good. So it cannot make the image sharp, for example. But it works really well. If you resize images on your iPhone, in any other app, this is what happens as well. Now, center crop takes this image with 256, smallest dimension, and one dimension that can potentially be larger. So if it's a really high image, this height dimension will be larger than 256, and it performs a center crop. So it always leaves out some of the stuff on the edges, and then if the image was really high, it's going to be cut off right at the center. And then we do normalize. So normalize, the numbers passed here are just the means and standard deviations for the corresponding pixel channels for red, green, blue. And we just pass them as constant because we don't want to go over the entire 150 gigabytes of images to calculate that again. It's a known data set, so these values are already known. But if you will do something like that with a different data set, you just have to do this once, do these calculations. And finally, this is how it looks like compared to the previous image, right? So first of all, the colors look a bit off because the drawing engine sort of expects the pixels to be from 0 to 1. So here it worked fine, but now we sort of normalize them to have 0 mean, which means some of them will be negative and the colors are changed slightly. This does not affect how the network sees it, but it does affect how our display image sees it. And finally, we cropped it a bit. So we can see that some ground here at the bottom got cropped off. This image is wider than it is taller, so it got sort of shrunk a bit. But other than that, it works. And this is the transforms that we'll have to do for validation. So for validation, for testing, for actually checking the performance of the model, we want maximum quality, we want determinism. So every time we apply the model to the image, we want to have the same result. And so this center crop and resize, like crop is probably a hack. It sort of uses the fact that the data set itself contains mostly images in the center. And because of this, we can afford to just crop out some stuff on the edges, and it still works. And then when we'll do training, we'll instead go for different augmentation techniques. So we wouldn't want to have the same image every time we see it in different epochs. Instead, we'll want to modify the image a little bit to provide more variety of the data and to make sure that the model does not overfit, does not remember specific images. Right, and now that we have our batch, let's try to apply the model to this batch. Model from X to device. Right, so it works. So it works. This is good. This means that we can now go over the model layer by layer and try to understand what is happening. So the shape is 32 by 1000. So 32 is just our batch size. And then the model is supposed to predict out of 1000 classes. So the output is has the dimensionality of 1000. Now let's look at the actual model code. Right, so this is how we initialize the model. torchvision.models.resnet 152. And this is the source code for that function. Now we can see that it can get some optional arguments that none of them were specified by us. It might get weights, the pre-trained weights that will be used by the model later. Other than that, it calls the underscore ResNet with the bottleneck block, and these are the actual layer sizes. So let's just move on to that. This one again performs some checks on the weights, and then it calls the ResNet class. And so ResNet class is something that we have worked with before. Sorry, not the ResNet class, but just the class that inherits from nn.module. We have worked with that before. This is how you define your own model in PyTorch. So here it has a bunch of parameters. Most of them have default values. It basically uses two main functions. So init sets up the layers, and then forward actually calls the model. So here the actual function forward calls the forward impl, and then the forward impl calls a bunch of stuff. So here is like the broad overview of the model itself. So it starts with a bunch of images, applies convolution, BN is batch normalization, ReLU activation function, max pooling, and then 4 layers, where each layer was defined by one of these functions. And each layer might contain like up to 36 actual intermediate layers, like convolutions. So the first thing I want to do now that the setup is working, I can actually get prediction from the model, is to go through this code line by line, apply the corresponding layers, and just check the shapes of the predictions. So I would say x1. Let me move that here. I'll not execute it, I'll just refer to it. Right, so let's say x1 is model.conv1 from big X, and then to device, and then let's check x1 shape. Yep, so this works. Now I'm going to print out the shape so I don't forget it. and here I say x1 shape, and then do the same for all the other stuff. Right, there it is. So let's sort of go over it, right? So we start with this little block. We get the basic input image, which is, let's bring that as well, x.shape, which is an image with 3 colors and 2 to 4 by 2 to 4 pixels. Now we apply the first convolution, and let's look at how it looks like. So the first convolution uses kernel size 7, so it's a big convolution, it's quite a big one, and then stride of 2, which means that it is going to shrink the image down by half. And this is what we see here. So the image has shrunk to 112 pixels, 112 by 112. Then we apply batch normalization right after the convolution. Then we apply, and the dimensions do not change because of that. Then we apply rectified linear unit activation, which again does not change the dimensions. Then we apply the pooling layers. So the max pool again uses kernel size 3 and stride of 2. So it shrinks the image by half again. Then we apply our 4 layers, layer by layer. So let me just quickly look at layer 1, for example. So layer 1 consists of 3 bottleneck blocks. The first one, bottleneck, is a convolution followed by batch normalization, followed by convolution, followed by... No, sorry, this is not how it is called. This is just the definition of the layer. So I better go for the definition of the bottleneck here to actually check the forward implementation. Right, and here it is. So the bottleneck performs convolution, batch normalization, rectified linear unit, convolution, batch normalization, rectified linear unit, again convolution, batch normalization. Then sometimes it might do something called downsampling. Then it adds this identity, and then again rectified linear unit, and then it returns it. Whew. So this is a lot of stuff. So let's sort of go over this again, right? I'll come back to my sort of forward implementation for the entire model. So these 4 lines here, this is typical for a convolutional network. So we apply convolution, we apply batch normalization on top of that to normalize the result. We apply the ReLU activation function as our nonlinearity, and then we add an extra max pooling to shrink the size of the image. And in this network, we only perform this once to basically shrink initial image by the factor of 4. So we started with 2 to 4 by 2 to 4, and now after applying this initial convolution, batch normalization, ReLU, and pooling, we get to an image of 56 by 56, but this time with 64 channels. Next layer does not change the size of the picture, but increases the number of channels by 4, by x4. Then it shrinks down to 28 by 28, and again increases the number of channels by x2. Then it shrinks down again and again. And so in the end, we have this 7 by 7 picture with 248 channels. And then in the end, we apply average pooling, collapsing all of these channels into one. And then we do flatten and just feed that into our fully connected layer. and that output of that layer is the output of the network. Right, so again, this first little detail is more or less close to how it looked like in other networks. This one is a bit different. So this first initial block was basically used to shrink down the image initially. And now each of these layers basically contain a certain number of these blocks. So let's go over this in the code. So bottleneck, right? So the convolution used here can be conv 1 on 1, conv 3 by 3, and then sometimes we have this downsample. So let's discuss like what is happening here. First of all, the 3 by 3 convolution. Before ResNet, people sort of thought that having bigger convolutions effectively increases the reception field of the convolution. So you might want the convolution like 9 by 9 or 7 by 7 to be able to capture really big features, like what if it's a specified corner or shape that just takes a lot of pixels. And so they tried to insert various sizes of convolutions. And some models like Inception actually had a bunch of convolutions applied at once, like 3 by 3, 7 by 7, 9 by 9. And then the result is basically the concatenation of all the outputs. Now, one of the novelties here, it wasn't actually invented in ResNet, it was invented in one of the previous networks. But the idea behind this is that you can look at several 3 by 3 convolutions applied one after the other as effectively communicating to each other and increasing this receptive field. So if the first convolution will have this receptive field of 3 by 3, after you have applied a second 3 by 3 convolution on top of that, this already increases the size of the receptive field. And you can just keep doing that to increase it even further. So if you have a lot of these convolutions stacked one on top of the other, you don't need to worry about bigger convolutions initially. You can just say that I'm only using 3 by 3 convolutions in my network. And if the network is deep enough, it will figure it out. And I think it is important because it simply narrows the search space of hyperparameters that you have. Because, you know, you don't need to think about any other convolutions. You just say that I'm going to use 3 by 3 and nothing else. So it's helping to sort of limit the number of experiments that you try to run to find the good architecture. Then another thing is the one-on-one convolution. So, like, what is one-on-one convolution? Is it just, you know, the identity transform that is not really doing anything? So not exactly. Many of you have seen this picture. I had this picture in one of my previous videos as well. So this is an example of 3 by 3 convolution that converts 6 output channels into 16 output channels. So it has this 3 by 3 receptive field. So it performs the convolution on the 3 by 3 square of pixels to get this pixel. But then if you sort of look at this picture from the top, what you'll also see is that every channel in the incoming image is connected to every channel in the output. So there is a lot of connections there. I realized how many there are by just drawing all of them. There's a lot of them. So each of these 16 output channels is connected to each of these 6 input channels. On top of, you know, this 3 by 3 matrix here, right? So every pixel here has this extra lots of connections, and each black line here corresponds to the actual parameter in the convolution that we are going to optimize for. And this is 3 by 3, right? So if you turn this into a 1 by 1 convolution, it basically will have this 1 by 1 small receptive field, but it will still have this loads of connections that connect various channels between each other. So you can think of one by one convolution as something that does not propagate spatial information, so it does not connect neighboring pixels to each other, but instead it just increases the complexity of the function being performed on the image by, in similar terms, as just a dense layer, right? So it basically takes input pixel, takes output pixel, and then performs a fully connected layer computation just within that pixel. So it's basically a way to add complexity to the function being approximated just within this one pixel. And so in this regard, 3x3 convolution can actually be thought of as doing two things at once. So it applies a function, increases the complexity of the stuff that we try to predict, as well as, propagate signal between pixels. And the actual fully connected layer, if it is applied here, in addition to connecting every input channel to every output channel, will also connect each pair of pixels to each other. So it's just, computationally unfeasible. And so, yeah, with 3x3 convolution, you'd have 3x3 by 6 by 16 parameters. And then with 1x1 convolution, you get this 1x1 receptive field, but still 6 by 16 parameters. So 1x1 convolution can be thought of as just some function applied to the input. Right. Now, let's look at the code again. And yeah, apart from the first 7x7 convolution that we've seen that just performs the initial processing of the image, all the other convolutions in ResNet are either 3x3 or 1x1. Now, what about this downsampling here? Like, what is it? So, and what is this plus here? So this is ResNet. Like, one of the primary novelties in this model is the residual connections, the connection that I've talked about in my previous video. So it should look like just output being added to the input, right? So identity here is the input, and we can see that this is what is happening sometimes, but not all the time. And the reason for that is because if we look at the sizes that we've got here, so for example, the first layer that gets x5, it takes an image of 55 by 55 with 64 channels, and then converts that to 256 channels. And then second layer, apart from increasing the number of channels by the factor of 2, it also shrinks the image down by the factor of 2. And because of that, we cannot directly just add input to the output because they will have different shape. We cannot do that. Instead, we try to do this downsampling, and we can see the definition of downsampling here. Where is it? Yes, this is it. So it's n.sequential, which is just the concatenation of layers of 1x1 convolution with the normalization layer. Right, so here it is. In the first layer, this downsample is convolution that gets 64 input channels and 256 output channels. Kernel size is 1, so it's 1x1 convolution, and then batch norm. So it's basically just one extra convolution that lets you resize the input to the side of the output, to the shape of the output, and you would only have this in the first block within the layer. So if I look at, so layer 1 has just 3 blocks, and if I look at layer 3, for example, it has, let's see, it has 36 layers, and only first layer needs to do this shape transformation. So only first layer will do this increase of number of channels and decrease of number of pixels in the image, and all the other layers will just transform what they have. They don't really change the shape of the image. And by the way, they achieve this by having some padding, right? So if you just apply a 3x3 convolution, the image size will actually shrink by 1. And it's really not convenient from the code standpoint, because you might have variable number of layers in the network, or a variable number of blocks in the network. So it's really useful to have this padding that makes sure that after every convolution, the shape of the image, of the input and output image, are actually the same, unless you want to explicitly downsample it. And so this allows you to stack as many such layers on top of each other as we want. Right. And so, again, to compare that to our initial set, for example, main difference here, so the initial set was convolution, batch norm, ReLU, and max pooling. So main difference in these layers here is that they do not use any pooling. They perform the downsampling by just applying the convolution with 2x2 stride. They don't have any pooling, and then we apply a lot of them. So most of the layers of these networks are within these 4 big segments, I should call them. And then in the end, we apply the final average pooling, flatten, and the fully connected layer. So this network has only one fully connected layer in the very end. And this is about it from like how the model works. Now let's just go over the code line by line to actually make sure that we can read it. We will have our own cleaner version of the code a bit later, because a lot of stuff here, is not actually used, but it is configurable. But let's just make sure that we can actually read that. So I'm going to start reading from ResNet 152. It was down here, right? So this is what we started with. So we are not using weights, so we can just skip through that. This one calls _ResNet. It checks the correctness of the weights. Again, we are not using that, and calls the ResNet. So norm layer is always PyTorch batch norm 2D. By the way, PyTorch. I was telling that this repository tries to follow the original paper, but it is not always the case. So we can see right now in 2023, the batch norm 2D actually has default momentum that was not invented in 2015, in the year when this model came out. So this is a slight deviation of this code with the original. But the researchers actually show that it works at least as good, so they just left it at that. So the norm layer is always this batch norm. In planes is basically the starting number of channels that we'll have, and then it will grow after every big segment. Dilation is 1, so we use defaults here, so we're not trying to dilate anything. Dilation is the process of applying convolution to only some pixels to save up on computational and to just throw out some pixels, for example. We're not doing this here. Number of groups is always 1, so again, we are not going to look at that. Width per group is then just the number of in-planes. This is the definition of this initial block that performs first shrinking of the image, and this is like the unique part of the model. And it has convolution, normalization, ReLU, max pooling. Now all the other segments all look pretty much similar. So this one creates a segment with 64 channels, then 128, 256, 512. And has the number of layers that were specified before. And let me just check once again this number. So it's first one will have 3, then 8, and then 36, then 3. So quite a lot. And each of the blocks also has like 3 convolutions. So I believe after multiplying by 3 and adding all the other smaller parts that we had, we will get 152 convolutions. All right, where was I? Right. So each of these segments called layers here is initialized using this function. So let's try to read it as well. So we don't use dilation, so we don't need to discuss this. And now here we say that, okay, if here the sort of the number of in-planes here refers to basically the variable that is being changed as I iterate over layers when creating the model. So it just checks, it's just a way to not explicitly write all the architecture line by line and just have a for loop that does that. And so I've started with 64. So as soon as I am constructing a layer that is supposed to output 256, for example, or something like that, it will check that it does need downsampling to modify the shape of the residual connection that we try to add, and it just adds this downsampling. Then the sort of primary component of this layer is the block, and the block for ResNet 152 is the bottleneck. And it's called bottleneck, by the way, because it uses these one-by-one convolution. So it can be thought of as, you know, the actual bottleneck that takes a lot of input layers and just sort of turns them into something smaller. But in here, most of these one-by-one convolutions actually have more output planes than input planes. Expansion is basically how much more channels will the output have as compared to the input. The rest, I think we've already gone over. So we basically define convolutions. So each block has one-by-one convolution, two one-by-one convolutions, and one 3x3 convolutions. And sometimes it will have downsample. So actually have more one-by-one convolutions than 3x3 convolutions. Right, I'm coming back here. So we have decided the layers. Then we do the initialization. And here we use the chiming normal initialization with the mode fan out. This basically makes sure that the variance of the gradients stays more or less constant during backprop. But it is not as important as it used to be before residual connections. Yeah, this is pretty much it. So this is how the model looks like. We have looked at all the intermediate outputs. Now I'm going to sort of write it down a little bit more cleaner with no configurable parameters, just in our code. And we start looking at the actual training code. So here is the same code for the model, but now it's sort of defined from scratch in Jupyter Notebook, similar to how we defined the networks before. It's basically copy-paste from the PyTorch repository, but now a bit simplified with less extra options and so on. And so I will leave a link to this in the description, so you can refer to it. We'll not go over this once again because we have done that already with the PyTorch code. And I just wanted to say that it's important to be able to do this as well, you know, to be able to define your model from scratch. For example, if you wanted to change the architecture a little, or just make sure that you know exactly what is going on here. So it's always good to have the option to just define all of that by yourself. And now I want to go over the training code. Now, the training code in the PyTorch repository is much more complex than the actual model code. So instead of going through the source code first, I want to show how it is supposed to work in the notebook. The sort of simplified version of it that doesn't have a lot of complexity regarding potential other networks that we're not looking at today, distributed training, and so on. So this is going to be the proper version of ResNet in terms of architecture, but the code will be simpler. And then we'll try to read the source code as well, just to help you, get started on that, and maybe you need that in the future. So before we start with the actual training code, we have one problem to solve. That is, we need the validation set. So if I look at my validation data once again, I'll see that it's not actually in the same format as the training data. So the training data had a folder with one subfolder for each class, and then inside that subfolder we had the actual images. In here, I just have one folder. This is how Kaggle does it. So if you just download the dataset from Kaggle, you just have this one dataset, one folder with all the images, and there is no way to know which class this is. And the actual labels for this are in the root of the dataset here. So if I open this file, it says that this particular image has this particular class, and the bounding boxes as well, but we don't need that now. So to deal with that, I wrote a simple Python script. So you call it like this. I'm going to leave the link in the description as well. So it just converts the format of this, of what we get from Kaggle, to the same format that we use for training. So it will just move images around to have image folder corresponding to class name, and then inside that the actual images. Right, now let's go from scratch to look at the actual training code. So now this is modified to be able to train the full model. So this is just some parameter definition. We'll see how we use them exactly a bit later. So let's start with the training code. So this will load the training data set. Now, before I was showing with the actual validation transforms that once again made sure that result is deterministic. So it is the same for every time we apply the transformation to the image. And it maximizes performance. So we want the best quality for every image. Now, during training, this is not exactly what we want. During training, we might want to modify images a little bit to make the data more variable, to prevent the model from overfitting, to maybe apply some transformations that we believe the model should be able to learn. So for example, convolutions, they implicitly contain the translation information. So if the object has moved from here to here, the convolution sort of already knows how to deal with that. But it does not apply to rescaling, for example. So if the camera taking the picture got a little bit closer, or if the lighting is a bit different, or if the angle is a bit different, this is not something that our architecture explicitly knows how to handle, but we can sort of do that in our data instead. This is just basically a huge area of experimentation, but the actual ResNet network used just one simple trick, to be honest. So one thing that we do is random resized crop. Let me just fetch the help for this. So random resized crop. So once again, for validation, what we did was we always took the centered crop. So we first resized the image so that the smallest edge is 256 pixels. Then we took a crop that is slightly smaller, leaving a little bit off around the edge, and also making it square. So we're always cutting off the sort of longest part of the image. Random resized crop instead chooses some random scale and ratio, aspect ratio. So instead of just always doing this central crop, it will decide that, okay, I'm going to take this part of the image, I'm going to make it a bit higher, so I'm actually changing the aspect ratio, and then making sure that the result is still this 224 by 224 square. So there is some randomness in this, And it will, instead of just always going for the center, it will choose random parts of the image. It will stretch it out a bit by height or by width. And every time we iterate over the data set, so every new epochs, the same image will get slightly different variation of this transform, which sort of prevents the network to just remembering the image. Apart from that, we do random horizontal flip, so basically mirroring the image. Again, for the classes that we have here, this is a safe transformation, so mirror dog is still the dog. It's not always the case in computer vision, so mirroring a letter might make it unrecognizable or change the meaning of a letter. But in here, it's safe simply because of how the dataset looks like. So apart from that, nothing has changed. So we add this random resize crop, random horizontal flip. Then we define train data loader. Then we have the thing called train sampler. So again, if you watched my previous videos, there we just sort of iterated over the data and always in the same order. This is not actually recommended for stochastic gradient descent, because the model will look at exactly the same batches of images every time, and that might sort of lead it to, always having the same, path or this gradient surface, and it might lead to weird effects. So instead, it's better to just randomly sample it every time. So every particular image will always be with random neighbors in the batch, and the order in which we see the images will be different every time as well. So it's good to shuffle. And the way this shuffling is implemented in PyTorch is that we have our data set, and the API to work with data set is just you provide an index, and the data set returns an image with that index, right? And here we're saying that we also have a sampler that will sort of, every time we iterate over this loader with a for loop, every time we request the next batch of elements, it will come up with random indices that we haven't encountered before in this for loop, and just request those. So this is how sampling is done. Then we load our validation set. So I've already ran the script, so it's already converted to image folder, to the proper format, and so I can just use the transforms that I had before. Right. And the next thing I want to do, right, because we are going to write quite a lot of code right now. So we have already, sort of wrote the transformation code. We downloaded our data set from somewhere. Now we are going to write the code to train the model. And before that, we are going to write the code to compute metrics. And so there is a lot of stuff that can go wrong. Like I could have downloaded the wrong data set, for example. So it's good to check that it works before spending a few weeks on training. And I'm going to do that by just downloading a pre-trained model. So this is a small one called ResNet 18, right? So I've downloaded it. And on PyTorch website, on the hub, we can actually see down here that the expected error rate on the validation set of Imagenet. And so ResNet 18, the smallest model, is expected to have something like 11% error rate. So, and we'll just start by checking that, our model, the pre-trained model does have this error rate and not more. Thus, making sure that the data set is correct, the loading code is correct, and metrics calculation code is correct. So we'll get there. Now, before, in like simple tutorials, you probably have seen the cross entropy loss and then the SGD optimizer. Apart from that, we also now have momentum. I've talked about momentum and weight decay in one of my previous videos. And it's easy to specify them. You just initialize the optimizer with these parameters. And we also have the learning rate scheduler. So we'll see how that works now. So my initial learning rate is just 0.1, which is quite high by the deep learning standards. So how scheduler works is basically, if we scroll down to the actual train loop here. So again, this is quite similar to what we have before. So I iterate over like 100 epochs. I perform one train step that looks at the entire data set, basically iterating over the entire data set and doing the stochastic gradient descent. And then I call alert.schedule.step, which basically says that, one epoch has passed, update the learning rate. So this particular scheduler is initialized with step size and what is called gamma. So step size is 30 and gamma is 0.1. So what this will do is it will start with the learning rate of 0.1, which is a lot. It will train the model for 30 epochs. And then once 30 epochs has passed, the learning rate will be multiplied by this gamma. So it will be 10 times smaller, basically, 0.01. And then the model will be trained for 30 more epochs and so on until we finish training. So this sort of gradually decreases the learning rate, allowing the model to converge closer to the minimum. And this is it is a thing that is outside of optimizer itself, but we initialize this alert scheduler by passing in the actual optimizer. So optimizer and scheduler sort of talk behind the scenes once you do this schedule.step method. Right. Then, I make sure that model actually works. Again, this is an important checking step because I could have chosen the wrong size for the images, for example, or downloaded the wrong model. If I am able to compute the loss function, then something is at least more or less correct. So you should always check stuff like this because it's easy and it saves you a lot of hassle. Then I have my trainee loop. So this function performs one epoch. So it gets the data loader, which is just something that I'm iterating over. So this one for loop will iterate over entire data set, over entire 150 gigabytes of data. And so this one should be pretty standard. So I copy my images to device. I compute the predictions, compute the loss. Then I call loss.backward to compute the gradients. Then I perform this step of the optimizer. So it actually updates the parameters. In the end, I have the zero grad. And then sometimes I would report some metrics. And I report them by just printing out to the console, as well as pushing some data to my tensor board. So this is pretty much the same as it was before. Then for testing, the only thing that changed here with respect to my previous tutorials is the top 5 accuracy. So testing loop looks at the entire validation data once and computes some metrics and also prints them out to console and to tensor board. And I just calculate accuracy myself using tensors. So this correct is basically top 1 accuracy. It says whether or not the actual prediction of the model, top 1 prediction, corresponds to the true label. And then I also calculate top 5, which is, did the model in the top 5 predictions actually had at least one correct guess? And usually results on Imagenet are compared by top 5 accuracy. Right. And so here I am just calling the test function once on the model that I just downloaded on the pre-trained model. Again, to make sure that the accuracy is as expected. So top 5 accuracy is 89%, which is like 11% error rate. And then the official PyTorch hub says that it should be around 11% error rate. So it seems more or less correct. It has like 0.3% difference, so maybe I do have some problems there. I'll need to check that later. Right. Another important thing is the checkpoints. So we need checkpoints to save the final result, the final model. That's one thing we need it for. Also, if we are going to train the model for a few weeks, something might go wrong, like, your kid switching off the computer or something like that. And you don't really want to lose the progress. So it makes sense to save intermediate results as well. So, and it's quite easy to do that once every epoch. So, and it's easy because you need to save a lot of stuff if you want to do this in the middle of epoch. So, for example, the train loop sort of iterates over the data loader. The data loader has seen some images, but then not the other images. So and they are shuffled randomly every time. So you will need to save this sort of state somehow, like all the indices that you have seen, but not the ones you have not seen, and so on. So it's a bit harder. It's easier if you just save progress every epoch, because every epoch is sort of start from scratch. But you'll still need to remember to save the actual model, the optimizer, because optimizer keeps the momentum calculations, so it has some state that you need to be aware of. And this is important because if you forgot to save optimizer and then start from scratch with existing model, existing epoch, but a new optimizer, it's just some unexpected thing that might have affected your training somehow, and you wouldn't even know that happened. So it's important to be aware of these things. So I also need to save the learning rate schedule because it also has a state. Then just the epoch so that I know which epoch this checkpoint came from. And then the actual parameters. So this is why I defined my parameters in this way. So here I basically create the class that has the all the parameters that I need as just class fields so that I can access them, like params.batch size, for example. And then this wrapper override basically means that I can call params like just params, and it will just be converted into something like a dict, which is what I want when I save the params. And so this allows me to save my parameters to checkpoints as well, so that, if I have a random checkpoint somewhere, I don't really know what's happening there, I can always look and see which parameters it had. And to save the model, save all of these states, I just call torch.save. So torch.save basically saves anything. You can pass any Python object here and it will know how to save it, which is really easy to use. And from the actual model, I'm just saving the parameters. And this is important, like this is the recommended way from PyTorch. So we are not saving the architecture of the model because we have just defined that, which means that if we load the model, we'll need to have the same code written to do the same prediction. Because encoding the actual, like saving the actual code is harder because you might have some various if conditions in there. You might have your own custom logic. It's not always trivial to serialize that to save it to disk. But since you already have the code and you're not hopefully losing that, you can just save the weights of the model and then it's all trivial. So I'm saving the checkpoint once after every epoch. So right after I have trained for one epoch, I'm going to save the checkpoint, and I'm going to save like this checkpoint.pth will always have the most up-to-date checkpoint. And then I also have all the history. So model_1 will have the data from the first epoch and so on. I'll have like 100 of those, just in case I want to come back somewhere. Right. So this is what I do in the training. And then if something went wrong, if I had to restart my computer, before starting training, I would need to load the state of the model, the state of the optimizer, the state of the learning rate scheduler. So this is what happens here. Right. So now that all that is done, the last thing I want to do is to actually make sure my model is now, the one I'm supposed to define in the code. Again, making sure it works, and then just training the model. Let's see if it actually works. So the prediction works. Now let's just wait for the train loop. Right, so it has started. This is how it looks like. So in my train loop, I also report the number, the time it took to train for 100 batches, and the approximation of how long will it take to train the entire epoch. So this 6,000 seconds is roughly 2 hours. So you can say 2 hours per epoch, 100 epochs. It's going to be a long time, like a couple of weeks. So now let's try to see what we can do to at least understand what is the slowest part, because you might have some surprises there. So the way I did it, like one of the ways to do that is to just check your CPU, GPU activity during training. So first of all, check that device is GPU. So in my case, I'm MPS for Mac. It definitely should be GPU if you're training on one of the NVIDIA GPUs and so on. If it is not, you will have to go through the driver installation to make sure PyTorch works correctly and knows about it. So the way we check it is here. So you can just run torch CUDA is available, and it should be true if you actually have a GPU and it is properly installed. And when it is training, you can just go ahead and see the load on the GPU. So right now I stopped training, but you should expect to see a number close to 100% here for some Python process that does the training. If it is not close to 100%, that means that the bottleneck is actually somewhere else. And we can sort of try to understand where it is. So like one of the easy ways to understand this is just to try to throw away some stuff from the training. So here is my training function. So it does plenty of stuff like copying to device, actually computing the loss, updating the model. Let's just delete all of that. Let's call this blank train, and just leave the reporting in place like this. So I've removed everything, pretty much everything, apart from just iterating over the data loader. And now let's run and see how well it does. Train. So the train itself took roughly 6 seconds per epoch. So now, and you can look at the process of training as a combination of series of steps. So first we load the data, then we transform the data, then we copy it to the GPU, and then we actually apply the model, compute the gradients, and so on. And all of that is supposed to happen on the GPU. So here I see that just the loading process takes about 1.5 seconds instead of 6 seconds. So it's probably not a bottleneck. and this is on Mac. So on my actual desktop PC with the proper GPU, the story was different. So the actual bottleneck was in just data loading, because the GPU is faster and the disk is slower. So let me go over like how you can optimize the input pipeline. So let's go to the definition of our train loader. Right. So we start by defining a dataset. And dataset is just like a wrapper that does not really load the data from disk when it is created, because it will not fit into memory, but it knows where all the files are, and it receives an index and it knows where to fetch the corresponding image. And then you have the data loader. The data loader is the thing that will actually iterate over the trained dataset. In this case, it will also have the random sampler, so it will generate random indices for the next batch. It will load those indices, load the actual images, then apply the transforms, and then you'd get that as an X and Y in your for loop, right? So we also have the parameter num workers here. So, and this is how it works. So if I say that it is 0, what will happen is, let's imagine that you do some actual stuff here, right? So every time you need to fetch the next batch in the for loop, you would wait for it to load. So if you've done some work here, you jump over to the next iteration, and now you ask once again the loader to load more data, and you have to wait for the loader to actually load the images from disk. So it will be like sequential operation. You do loading, then once the loading has stopped, you do training for this batch, then you do loading once again, and so on. And obviously it's not very effective, because while you are loading the data from disk, the GPU is not really used, CPU is not really used, and so on. Now, if I say that num workers is 1, what that means is that now the data loader will try to do preloading. So although it's not explicitly written in any way in the code, when I iterate over the loader, it will see that, we get some batches from it, and it will try to keep a buffer of loaded batches and try to load it in the background. So now the training will not be sequential. So I will, when I'm doing training on the GPU, the loader already tries to load some more data in the background, which means that most likely, if the actual loading is done with enough speed, when I get to the next batch and I request the next batch from the train loader, it is actually ready to use. So this will basically make the loading pipeline and the training pipeline, make it run in parallel. But the loading pipeline will still have just one worker. That is usually enough for just disk operations, because you can't really speed the disk up with multiprocessing. But you also have transformations here that might take some CPU. So if the transforms are too heavy, that might mean that one worker is not enough to transform new images with enough speed. In that case, you might go for something like 16, which means that you'd have 16 workers trying to load stuff from disk in parallel and try to transform the images on CPU in parallel, and all of that happens in the background of your actual train loader. So this is definitely a useful parameter, really easy to use. Right. Now we also have this pin memory parameter. So what it does is it basically prepares the data that you are loading to be copied to the GPU. So there are some complications in the copying of the data. So the actual CPU uses what is called virtual memory, and because of that, and when you copy some data from CPU memory to GPU memory, you can't simply use the same virtual memory with pages and so on. So you have to first copy it to the so-called pin memory in CPU, and then copy it to GPU. Which means that if you just have your variable on CPU somewhere, you'd have to copy 2 times to start using it on GPU. Luckily, we have this train loader that does a lot of stuff in the background. So we can say that it should do this one extra step of copying as part of the loading pipeline, which means that we will have some buffer of data that is ready to be consumed by our training loop. So again, this speeds up the process. But it might take a bit of extra memory if that is your constraint. Right. Now, yeah, and one of the things that explains why this data loader is so often the bottleneck is that it tries to load images from disk in random order, which is not good. Even for modern solid-state drives, if you just check in Google the actual throughput in megabytes per second that you get from solid-state drive from just sequential reads as compared to random reads, you would see that random access is at least 10 times slower. And because of this, we always load random indices. So we keep requesting random files from the system. They are all stored in random order, so it's not very effective. So if the loading pipeline is still your bottleneck, you might consider some alternative approaches. For example, loading all the data from the archive or something like this. So it's not easy to do with the actual dataset API, because the dataset API sort of implies that you are going to be loading the data in random order, at least if you want it shuffled. But there is a new API currently in beta in PyTorch that's called Data Pipes, I think, that is more suitable for the sequential reading. Another issue that often comes up is the lack of GPU memory. So GPUs are usually really fast, much faster than CPU in training, but they have smaller amount of memory that we can use. And like GPU memory is one of the primary considerations when actually choosing the GPU. So here is how it looks like. So I've tried to apply my model to a batch of 64 images. And so it just dies with an error that's on Mac that says MPS backend out of memory. And I also printed out the shape of one of the outputs of the layers. So we mostly keep stuff related only to the current batch in GPU memory. So we don't store all the data set in there. We don't store the buffer from data loader. We just store the model and all the outputs that we need to compute the predictions and the gradients. And usually there are 2 main contributors to the size of the model. And depending on the architecture, the sort of ratio of these contributions will be different. So the first one are just model parameters, and the second one is the actual outputs. So here I've printed out the shape of one of the outputs. So it's 64 images with 256 channels, and then the image itself is 56 by 56. And this ends up being 51 million pixels. So if every pixel is a floating point number, it takes 4 bytes. So that would take roughly 200 megabytes. That's just one layer. So 200 megabytes, that's one layer. And so we have 152 of those. That will be probably 30 gigabytes. So that's quite a lot. It's actually much more than the number of parameters, right? So the number of parameters does not depend on the patch size. So the same layer, the same convolutional layer with 256 input channels and let's say 512 output channels will only have 3x3 convolution and then 4 bytes per floating point number. That's only like 5 megabytes. So 200 megabytes for layer output and then 5 megabytes one layer parameters. So for convolutions, it turns out that the actual size of the output dominates the size of the of everything we need to store, which means that we can actually affect that with the batch size. So the batch size was 64 here. So if you're out of memory, if you don't know what to do, you can try to reduce the batch size. At some point, that will start to affect the quality of the model because batch size affects how stochastic gradient descent converges. But, 16, maybe 8 images per batch might still work. That might still allow you to train this model. Otherwise, you'll just have to look at bigger GPUs or buy 2 of them and do distributed training. So this is like one of the primary concerns that might limit the sort of complexity of the model that you can afford. Apart from that, so I've done the actual training on my desktop. It took roughly 1 week. So we can look at TensorBoard for it. So this is how it looks like. So here are test accuracies for a couple of launches that I did. So I tried a ResNet 18 first and trained it pretty much to the end. So that's the gray one. And we can see that it took roughly 1 week and it went up to 89% accuracy, which roughly corresponds to what the PyTorch hub says it should yield. And the blue one is the big ResNet 152. It's currently under trained, so I still need to wait for some time for it to train. And it is at 87% accuracy. So it is still ongoing actually. But it's good that, if you have your computer, that you can afford to just have it running 24/7 and you have a week of time. Like you don't need to control it, it just trains there. And you can do that. And it's usually much cheaper than buying resources from Google Cloud or something like that. So now I want to take a quick look at the actual source code for the training as well, just to show how you can start reading it. We'll not dive too deep into it because the video is getting too long anyway. So let's go here. So again, I got to this repository by just Googling PyTorch ResNet. I get to the PyTorch hub, then I get view on GitHub, and I get the actual model code. Now to get to the training code, I go to the root of the same repository. I go to references. In there, I see a lot of stuff for different tasks like stereo, detection, classification. So we need classification. So the README here states the actual launch parameters and default launch parameters. So batch size, epochs, learning rate, momentum. Now, if we look for ResNet here, it doesn't really specify anything else. But then for some models, the parameters would be a bit different. So the RegNet, which is a different model, overrides some of these parameters. So it has some extra features during training. Now, if we go to the actual train.py, this is the main script that does the training. So down below, it has the list of arguments. Again, many parameters are not explicitly stated in the README, and they are just stated here. So for example, the optimizer. Default optimizer is SGD. So if nothing is said in README regarding this model, then the optimizer will be SGD, stochastic gradient descent, and so on. So this function defines all the parameters and the default values for them. So when I'm reading the code, I'm constantly coming back here to check, if this parameter is enabled by default and what's the value for it. And then in the end, like what we actually do in the script, we just run the main function. And this is how it looks like. So it gets the arguments. You would need to have the data set downloaded and ready to use. Then load data is the function that handles all the dataset loading and preprocessing. So if we go here, it basically does similar stuff to what we did, but with a little bit more complexity. Because sometimes you'd have, like this script can work with distributed training, for example. Here we have dataset caching. Again, this is a useful thing. It is not caching everything because you can't cache 150 gigabytes of data. It's just caching the sort of high-level information, like the number of files of images in the dataset. So if you have noticed, if you just restart the training, it might take a couple of minutes just to initialize the dataset, even though it does not actually load images during initialization. And it happens because the dataset needs to know its total size. And for that, it needs to iterate over all the images and count their number. So it's a lot of sort of syscalls to iterate all the folders, count all the files, and so on. And so caching helps with that. But be careful here because caching saves the entire state of the dataset, including the transformations. So if you are experimenting with the transformations and you are changing something, don't forget to, change the cache as well. Then we get the actual data set from the preset. So let me just quickly go there. So it is located in the same folder in the file called presets.py. So they have two different presets for evaluation and for training. And here they basically define all the same transforms that we did to load the data. So they convert it to tensor, then do random resize crop, random horizontal flip. So in some cases, you might see that it has some augmentation. This is disabled for ResNet, but some other networks might use them. And here you can find examples of how to write that in code. Some useful augmentation transforms that can sort of change the image a little bit to make the task more challenging for the model, for example. Then for evaluation, it's pretty much the same, but now we have less number of transforms because we want to have consistent results instead. And that is the dataset loading function. So it has one preset for training, one preset for evaluation. Sometimes it does distributed training, but roughly it just returns the same sort of dataset, data loader, sampler, all bundled together into these variables here. So mix up cut mix is disabled by default. Here we have definition of data loader. We load the model. We define the loss function. So it's cross entropy loss, weight decay. The actual optimizer, and again, this is stochastic gradient descent by default, but it does have momentum and weight decay. Now we also have learning rate scheduler, and I actually learned how to use learning rate schedule by reading this code and then writing some experiments myself. And the default one is, I think this one, the step LR. So learning rate schedule is the thing that you call every epoch to notify the optimizer that, once every 30 of them, you need to downscale the learning rate, basically. So these all are false by default. Then sometimes you'll resume training, so you need to load the checkpoint. And then here is the actual training. So it looks pretty similar to what we did. So iterates over epochs, does one epoch training, performs the step of the scheduler, computes some metrics, save the checkpoint, and then train one epoch. Let's look at that. So it also has some metric logger, similar to TensorBoard, I suppose. Other than that, it iterates over the entire data, copies the images to device, zeros out the gradients. Sometimes they use something called scalar. Again, for ResNet, this is false. Compute the gradients, update the parameters, and just report some metrics. So again, I'm showing you so that you might build some familiarity with this code, and you might want to go there and just read code for some different model, for example. But for ResNet, it does all the same things that I've already showed in Jupyter Notebook, so we will not spend too much time here. Right, so this concludes the sort of code reading, the demonstration. So we have started training the model. It's good that we can do that with relatively low investment. It's one of the few machine learning tasks that is actually available like this. That's why I like computer vision. And I hope you have seen just how much more complex the real thing is, the actual model that can beat a benchmark on a big data set, how much more complex it is compared to just concepts and tutorials that you might have done before that. Now, I just want to briefly go over the results of the entire model, basically. So we've discussed before that the competition ran from 2010 and 2017. In 2017, it was closed because models basically started performing better than the humans, at which point training them on human labels became sort of difficult. But also, the actual error rate is still 5% even for top 5, meaning that out of 5 predictions, in 5% of the cases, there's still not even one correct one. But it's also important to try to look at these predictions, like what is actually going on there. Is the model, confusing horses for teapots or something like that? And if you actually look at that, there are different sorts of errors. So here is one from the actual paper. This is from the Chiming initialization paper, so the one before the ResNet paper. So here we want the model to identify the letter opener. And here I think it's pretty unclear what is actually what the girl is holding here. So it does look a bit like a wooden spoon, like a drumstick as well. So I wouldn't say the model did too bad in these cases. And here is a different one where we want the model to identify this as a spotlight, but actually the image has a lot going on. So it has a piano, it has a chair, and the model sort of correctly identifies that. But, it doesn't say that it is a spotlight, so it still count that as error. And this is, I should say, the problem with the data set itself. So one problem out of this is that we always want just one prediction per image. So we are not letting the model say that, this is a picture and it has both a piano and a chair and a spotlight. We're just not giving the model the opportunity to do so. And it might also hurt our training, because when the model does this, when the model does predict that there's a piano and that there's a chair, although it is right, we're still saying that it is wrong.
we're propagating the gradients as if the model just made a mistake, which might just confuse the model. So that's a bad thing. And another potential problem is that the data set itself is quite limited in the sort of overall style of images that you might expect, right? So, and it always happens that once you feed unseen data to the model, something with completely different style, like here from comics, from the cartoons, or from artwork, or maybe just from a completely different camera, like one of those self-driving cars with colors looking completely different and resolution being different. And the model might start to give unexpected results. And so this one is from ThawSpark. And you can easily get results like this for a pre-trained model by just going to PyTorch Hub. And you can see the model demo here. So it leads you to Hugging Face. So you can look at one of the pre-trained model here and just upload the image and see what the output is. And so for this image, it says quite surely that it's a pencil sharpener, and obviously it is not. So we don't know what's going on here. Maybe the model has no ways to express it. The model actually has quite limited set of classes. So Imagenet 1K, it's a subset of Imagenet, and it doesn't have a class for person, for example, or for horse, but it does have a few breeds of dog, for example. So it might not have the means to express what it sees here. Or maybe it is just so used to seeing the specific pixel patterns that come from high resolution colored camera. And then if it sees something with just a slightly different pixel pattern, like a cartoon, so the objects look similar to human eye, but then on the actual pixel level, they are completely different. And since the model haven't seen anything like that in the training, it might just give random results. And this is another bad thing. Like, we're not training our model to say, sorry, I'm not sure about what is going on here. I'm just not going to predict anything. There is no way for the model to even express that. It always have to output class probabilities. And so in this case, it will just say something random, which might not be good, might not be what you want. So in the next videos, we are going to cover sort of more ways for the model to express itself. And they are also useful for the actual, uses of computer vision. So we are going to look at Coco Dataset. That's the famous one that is still up and running. So it's alive and well in 2023. So we'll look at object localization and detection. That is basically drawing these bounding boxes for objects in the video right after this one. And then later we'll start digging into object segmentation. That is finding out the actual pixels that belong to the class or to the actual instance object. And finally, to text description. So Coco Dataset actually has a proper text description for this image. So it says something like cowboy with a few sheep and a dog on the field, and something like that. So it sort of gives the model more ways to express itself. And it might really be useful for computer vision tasks. Like, think about generative AI, for example. You don't provide a class label for the model to generate something. You have a prompt, like, generate me a picture of a dog that looks like this and this. So having the model being able to sort of work with text is really useful in terms of what we can ask from it. And if you think about this is actually a complex task because, how do you even represent text as a model input? So with images, it was pretty simple. You can just feed in raw pixel values and you get this sort of fixed length vector of floating point numbers, which is just what we want as an input to neural network. How do you do that with text? So we have a lot of ground to cover. So hope to see you again. See you soon.